Hi everyone. So we're going to start by talking about trig identities. So chapter 5, section 1 is all about trig identities. Let's start by talking about what is a trig identity. So notice here it says the symbol equal sign. It means several different things in math. So we've talked about a true sentence. You could say that 1 plus 1 equals 2 is true because it's, the meaning is the numbers are equal. This is a true sentence, number 2, because again, they have equivalent expressions. But take a look at number 3. That's actually called an open sentence. An open sentence can be true, it can be false, depending on whether x is a solution. For example, if you substitute -1 into both sides of the equation for x, the sentence is false because if you put -1 in for x, 4 is not equal to 7. Okay, so an identity, here's number 4. That's actually an identity. Identity is a true sentence with a very important qualification. So it's true, just like 1 and 2, but that has a very important qualification that x must be in the domain of both expressions, on both sides of the equal sign. So if either side of the equality is undefined, the sentence is meaningless. So for example, if you substitute -1 into both sides of the equation in number 3, you got 4 does not equal 7. False. But if you substitute -1 into both sides of the identity, number 4, you get a sentence that is meaningless because, again, you cannot divide by 0 because if you put -1 in for x plus 1, you get 0 in the denominator. So that is meaningless. So we're going to talk about now, I think it might help if we talk about another example. Cosecant theta equals 1 over sine theta. That's a trigonometric identity because it is true for all values of theta for which both sides of the equation are defined. So the set of all such values, that's called the domain of validity. So for example, the domain of validity for cosecant theta equals 1 over sine theta is all real numbers except theta equals pi k, because again, if the sine of theta equals 0, 1 over 0 is undefined. So that's how now we know what an identity is. So why don't we go ahead and do some examples. Now we are going to use all of the identities on this list. So let's start talking about, and I know we've talked about basic identities, and we actually have talked about the first Pythagorean identity, and we've proven that in the past. So now let's go ahead and derive the other two Pythagorean identities. So for example, if you know that cosine squared theta plus sine squared equals 1 is an identity, for example, then any manipulation of this would also be an identity. It would also be true. So we know that cosine squared of theta equals 1 minus sine squared of theta, etc. But what we're going to do right now is we're going to take cos squared of theta plus sine squared of theta equals 1. It is 1. Sine squared over cos squared is tangent squared of theta, and 1 over cos squared of theta is secant squared of theta. So now we have our second Pythagorean identity. And what if we try this again, but this time we are going to in the Pythagorean identity cos squared theta plus sine squared theta equals 1 by sine squared of theta. Our third trigonometric identity, that the cotangent squared of theta plus 1 is equal to the cosecant squared of theta. Okay, so what we're going to do right now, before we jump into simplifying our trig identities, we're going to actually think about a word example. So Lewis Carroll actually invented a game, it's called a word ladder game. A word ladder puzzle begins with 2 words, and to solve the puzzle, you must find a chain of words to link the two in which 2 adjacent words differ by 1 letter. So we are going to change maize to gold, and the whole idea is to do this in as least amount of steps as possible. And again, with each subsequent step, you can only change 1 letter. So go ahead and pause the video and give it a try. Okay, hopefully you paused the video and you gave it a try because I don't want to spoil all the fun. But again, if you changed 1 letter, but again, the trick is it has to be a real word. So if you change Z to L, that's a real word, male. Then let's see, you could change the A to an O. And then you could change, you could change the E to a D. And then you could change the M to a G and get gold. So there you go. So that example is hopefully going to help you a little bit with our trig identities, because often it's possible to use identities and algebra techniques to simplify complicated trigonometric expressions. I will show you what I mean. Okay, so And as we go, maybe we'll write some strategies over here. So I'm going to look at that first expression. And again, whenever I see something that's squared in there, I'm thinking maybe I might use a trig identity. So what we're going to do is try and make this look a little bit simpler. Another strategy is to factor. So notice I could factor out a sign from each of these two terms. And then you're left with sine of x times sine squared plus cosine squared. And I know sine squared plus cosine squared is an identity. That's 1. So I just simplified it to sine x. And again, similar to the whole changing the word ladder, we're going to do one step at a time. Okay, so for b, I noticed that 1 plus tangent squared, that's an identity. If we go back here and take a look, 1 plus tangent squared, there we go, 1 plus tangent squared, notice that's secant squared. So I can replace 1 plus tangent squared of x with secant squared of x. And again, this is really helpful, I think, to practice a lot of your algebra. So now we have secant squared of x divided by cosecant squared of x. And another one of our strategies to change to sines and cosines. That can be helpful. So we have 1 over cos squared of x divided by 1 over sine squared of x. So that's 1 over cos squared of x times sine squared of x over 1. So this is actually just tangent squared of x. Okay, so we started with 1 plus tangent squared over cosecant squared, and we ended up with tangent squared. Definitely more simple. Okay, let's try the next one. You can distribute that 9. And again, whenever I see the squares, I'm thinking we're probably going to use a trig identity somewhere. So notice I kind of rearrange these things and move them around because again, if you go to the previous page, we have a trig identity that has a tangent and a secant together. Let's just write it right here. 1 plus tangent squared equals secant squared. So if I have secant squared of x minus tangent squared of x and cosecant squared of x, let's see, minus cotangent, we could also use our other identity, Pythagorean identity. Notice again, you can manipulate these so that if we have secant squared of x minus tangent squared of x, that's equal to 1. And cosecant squared of x minus cotangent squared of x, that's also equal to 1. So we have 1 plus 1, which is 2. Let's go ahead and try the next example. Here we go. For D, and we're going to add to our strategy. I'm going to erase that to get a little more space. So notice another strategy. What's more simple, 1 fraction or 2? Well, I would think 1 fraction. So you may want to get a common denominator to add 2 fractions together. So let's give that a try. So we have sine x over 1 minus cos x times sine over sine. So remember, you can multiply by a form of 1 whenever you want. We did not change the value by a form of 1. And over here, the second term I need to multiply by 1 minus cos x over 1 minus cos x. Now we have a common denominator. So I can write this as sine squared plus 1 minus 2 cos x, oops, not squared, cos x, plus cos squared all over my common denominator. All right, so I'm not going to distribute my sine x because I'm thinking something might factor. Notice we have sine squared plus cosine squared. That's just 1. So we have 1 plus 1 minus 2. We have 2 minus 2 cos x all over sine x times 1 minus cos x. And this is where our factoring is going to help us out, because if we factor out a 2, notice that the 1 minus cos x cancels out, and we end up with 2 over sine x, which is 2 cosecant x. Okay, let's do this letter E here. So letter E, again, you could use one of the strategies here. Go ahead and pause the video for a minute and think about what strategy you think would be helpful. Okay, so I'm going to try one of the strategies that I bet none of you really, well, I shouldn't say none of you, I bet that this maybe was not first on your list. I'm going to try factoring, because notice that both terms have a tangent x. So if I do 1 over cosecant squared of x and 1 over secant squared of x, notice that I have tangent x times sine squared x plus cosine squared x, which is really just a trig identity for 1, so I end up with tangent of x. So the factoring, I think, really came in handy. Okay, so speaking of factoring, now we're going to go down here for 8, and we're going to factor each expression. So the first thing you want to do, notice I have a sine and a cosecant in the same problem. So that's not very helpful. I would like to, cosecant is 1 over sine, so 1 over cosecant is the same thing as sine. And now for some of us, we might want to just jump in and factor. For others, you might say something like a is sine x, so we really have a squared plus 2a plus 1, and that might help you factor. And then you realize, oh, but a was really sine x. But some of you might be able to skip that step and go right to here. That's fine too. Okay, notice this problem has a sine and a cosine. Now that cosine, you are stuck with it, okay? But the sine squared, we could use an identity for that, because we know that sine squared plus cosine squared equal 1. So instead of writing sine squared, you can write 1 minus cos squared, because again, you could use any manipulation of this identity. So I know that sine squared is really just 1 minus cos squared. Okay, now we have negative cosine squared x plus 2 cos x minus 1. I think sometimes it's harder to factor something with a leading coefficient that's negative, so maybe factor out that negative sign. And we have cos x, and oh, and again, you could go ahead and do the substitution with the a, or just jump right in, whatever works for you. There you go. And we factored. Great job, everybody.